Features are the inputs that artificial intelligence systems use to make decisions or predictions. They represent how raw data is transformed into a form a model can process. Without features, data remains unusable. Understanding features is essential to understanding how AI systems actually function. Raw data by itself does not automatically convey meaning to a model. Features act as signals extracted from data, highlighting aspects considered relevant. This transformation step determines what information is preserved and what is ignored before learning even begins. Features matter because models can only learn from what they are given. If important aspects of reality are not represented as features, the model cannot reason about them. Learning is therefore constrained by feature design, not just by algorithms. A feature is a representation of some aspect of the world expressed numerically. Models do not perceive objects, people, or concepts directly. They operate on structured representations that stand in for those realities. An intuitive way to think about features is to ask what information the model actually receives. It never sees the real world. It sees tables, vectors, or tensors, composed of numbers derived from observations. Having large amounts of data is not sufficient. Data must be structured into meaningful inputs. Poorly chosen features can prevent learning, even with vast datasets and powerful models. Features differ from labels. Features are inputs provided to the model, while labels represent desired outputs or correct answers. Confusing these roles leads to misunderstanding how learning occurs. The choice of features determines what patterns a model can detect. A model cannot discover relationships that are not encoded in its inputs. Feature selection therefore shapes the limits of learning. From the model's perspective, reality is extremely limited. It has no awareness of missing context or alternative representations. Its understanding is bounded by the features engineers provide. Feature design involves human judgment. Decisions about what to measure, include, or exclude reflect assumptions about relevance. These choices embed human perspectives into technical systems. Numeric features represent quantities such as age, temperature, or income. They allow models to detect gradients, trends, and magnitudes. Their scale and range strongly influence learning behavior. Categorical features represent types or groups, such as product categories or regions. These must be encoded numerically before use, which introduces design choices about similarity and separation. Binary features represent simple yes or no conditions. While limited, they are powerful signals in many decision systems. Even simple features can significantly affect outcomes. Text must be transformed into numerical representations before models can process it. Techniques such as tokenization and embeddings convert language into structured feature spaces. Images are represented as pixel values or learned visual features. Models do not recognize objects directly. They infer patterns from numeric representations derived from visual data. Time-based features capture sequences, trends, or temporal context. When events occur can be as important as what occurs. Representing time correctly is often challenging. Contextual features describe surrounding conditions. In many systems, context dramatically changes interpretation. Without contextual features, predictions may be misleading or incorrect. Derived features are constructed by combining or transforming existing features. Ratios, differences, or aggregates can reveal relationships not visible in raw inputs. Feature engineering refers to the deliberate process of designing effective features. Historically, this required deep domain expertise and significant experimentation. In traditional machine learning, humans manually designed features. Success depended heavily on understanding the problem domain and anticipating useful representations. Modern deep learning systems often learn features automatically. However, this does not eliminate feature choices entirely. Data selection and pre-processing still shape learned representations. The key difference between traditional machine learning and deep learning lies in feature creation. Deep models learn representations internally, while classical models rely on explicit features. Good features are relevant, informative, and stable. They capture signal rather than noise and remain meaningful across different data samples. Bad features introduce noise, redundancy, or irrelevant information. These can confuse models, slow training, and reduce generalization performance. Missing features limit what a model can learn. Important variables omitted from inputs cannot be recovered through training, regardless of model complexity. Redundant features provide overlapping information. While sometimes harmless, excessive redundancy can increase complexity without improving performance. Feature scaling ensures that numerical values are comparable. Without scaling, features with larger ranges may dominate learning unfairly. Normalization and standardization are common scaling techniques. These steps improve training stability and model performance, but do not add new information. Features can encode bias. When features reflect historical inequalities or social proxies, models may reproduce or amplify those patterns. Because features influence decisions, they directly affect fairness outcomes. Responsible feature selection requires ethical as well as technical consideration. Model predictions follow feature representations. If features are flawed, outcomes will reflect those flaws. Regardless of algorithm quality, overfitting can result from overly detailed features. Models may learn noise rather than general patterns, reducing performance on new data. Sometimes simpler features generalize better. Reducing complexity can improve robustness and interpretability. Domain knowledge plays a critical role in feature design. Understanding the real-world system improves representation quality and reduces unintended consequences. Features are not neutral measurements. They encode assumptions about what matters, how it should be measured, and how it should be interpreted. Feature relevance can change over time. When real-world conditions shift, previously useful features may degrade, requiring monitoring and updates. Maintaining feature quality is an ongoing responsibility. Monitoring helps detect drift, degradation, or unintended effects before failures occur. Feature pipelines manage how raw data becomes model inputs. Errors or inconsistencies in pipelines can silently affect system performance. In production, feature constraints include latency, availability, and cost. Not all theoretically useful features are practical to deploy. Many system errors originate at the feature level. Poor inputs propagate downstream, affecting predictions, decisions, and trust. Transparent systems benefit from interpretable features. Understanding inputs helps explain outputs and supports accountability. Features enable correlation-based learning, not true understanding. Models associate patterns, but do not comprehend meaning or intent. Feature-based learning has limits. Some aspects of intelligence cannot be captured through static representations alone. Human oversight is essential in feature selection. Reviewing inputs helps prevent harmful assumptions from becoming embedded in systems. Trust in AI systems depends partly on trust in features. Stakeholders must believe inputs are appropriate and responsibly chosen. Features form the foundation of all AI systems. Without them, models cannot learn, reason, or operate. A common misconception is that features make systems intelligent. In reality, they only define the space within which learning occurs. The key takeaway is that models learn patterns in features, not in reality itself. Representation determines capability. By shaping what is visible to AI, features shape outcomes. Understanding them is critical to responsible system design. Next, we will examine what a model is and how models transform features into predictions through learning and inference.